total phosphorus was quite some scatter in years before application and also after, especially in 2011, 2012. In general, the median total phosphorus concentrations after application dropped to more or less half as what was measured before. There is a slight difference between the measurements after application and before flock and lock, because before flock and lock, these are mostly upper limnium samples, and maybe one depth just below the surface, and only occasionally there are samples from different depths of areas. After application, the entire water column has been sampled. If we look at the phosphate concentrations in this lake, there are some things that pop up. Well, first of all, there's a lot of green, which means very low phosphate concentration, below 10 micrograms per liter. Those low values were hardly seen in the period before application. It's already visible here in the period March until May in the application. Here it's mostly green, and there it's green, and there. Let's see here it's more orange colored. Nonetheless, there are also some periods of clear orange or even bluish colorings after application, and this means higher phosphate concentrations. And this can be related to certain events. This entire water column filling of phosphate, so this is not total phosphate, it's phosphates, is coinciding with a planetary rubescence bloom, which suddenly popped up in autumn 2010 and lasted until spring 2011. The very high phosphate concentrations in summer 2011 coincided with anoxia near the sediment, indicating some redox label phosphates being found there. And no discoloring occurred in the first summer, but then there was the high oxygen concentration measured near the sediment. Hypoxia occurred in 2010, 2012, also 2013. The planetary rubescence bloom, it came to us out of the blue, and it was there for a couple of months during winter. Cyanobacteria survived freezing in the ice, and they vanished, decayed, and vanished just before opening of the new bathing season. So they had no influence on the bathing activities, recreational activities later on in the system, in the year. Going to the sediment in this lake, after application of the flock and lock, there was a clear decrease in the phosphate release, and especially under oxic conditions. And over time, there's a nice increase visible in the amount of phosphates that are being released sediment. Or the difference between anoxic incubated cores and cores incubated with quite some oxygen in the water column are visible, and this is mostly caused by the amount of iron, perhaps also the iron we added to the lake. Under anoxic conditions, last year, the sediment phosphorus release equaled pre-treatment phosphorus release. Oxygen conditions near the sediment are still in favor of the lower release, but also there we do see an increase occurring. So probably it's a matter of time, a couple of years, before the system might switch back to a clear options, more eutrophic state. This reflects in higher chlorophyll concentration and more cyanobacteria. If we classify the lake, how it has been in the past and how it has been in the last couple of years, again plotting summer chlorophyll concentrations against summer total phosphorus concentrations, in black gray are the pre-treatment values, and in white the post-treatment values, leaving out the 90s years, as we saw for Lake Harbach, a clear improvement in the water quality of the lake. It moved from a eutrophic to a mesotrophic state, has been in that state for now for 5 years. So to summarize these results, the results we got in those two lakes, those two all lake experiments. First in Lake Harbor, actually the pictures are from Lake Harbor, like, give you an idea about the water transparency in the lakes there. In Lake Harbor, have been no blooms after treatment and low growth lake concentrations the whole year round. Strong phosphorus reduction is observed, and no hypolumian anoxia occurring. The transparency of the water is fantastic and is well, much appreciated by the scuba divers. The lake changed from a eutrophic to an oligo-mesotrophic state, and it can be viewed as that now already for 6 years. In Lake Baikal, summer growth rate concentrations are low, but we did have rather huge bloom of plankton rubescens in the winter of 2010 to 2011. Luckily, it appeared after closing of the bathing season and before opening of the next one, so it virtually went unnoticed to the authorities, and it was of no risk to bathers. But it was a bloom, which was a surprise to us, and we have no idea where it came from and what was fueling it. There have been no swimming bans there for already 5 years. The authorities are pleased with that, especially seeing the history of that lake, and it was changed from a eutrophic to a more mesotrophic state. So these two examples look promising, and we decided to explore the possibility of applying these kind of techniques also to more shallow systems and to other water types. This is just an example here of an experiment conducted in a pond, also in the southern part of the Netherlands, where compartments of 20 by 20 meters were constructed, and in which different measures were implemented. We have control, nothing happened, just making compartments. Compartment where the ventilator's fish was removed, indicating as fish stock. Compartment that received phosphorus and polonium chloride, just phosphorus were dredged, and to which polonium chloride was added to settle the resuspended sediment. And the compartment that was simply dredged. The picture is taken 2 years after the start of the experiment. So there are clearly clear differences visible here. Those 4 compartments that are aimed at tackling the internal loading are completely different than the control in the fish stock management and the ponds. Those two resemble the ponds. Here, submerged macrophytes are flourishing, and even floatable algal biomass can be observed, and the water transparency is much higher than it is over there. Ranging these again in the more water framing directive context, labeling them with an ecological quality ratio clearly shows that the pond could be considered of an insufficient quality over 3 years. So each bar is 1 year, 2009, 2010, 2011. The pond can be insufficient based on chlorophyll. And control, well, it's insufficient to moderate. Same for the fish stock management. But all other 4 reach an excellent status in second year. 2011, I should say, the 3rd year in this. So really pointing to that it's possible to improve the water quality when in these situations. Internal loading is a major issue. Ecological quality ratio doesn't distinguish itself. Well, in all 4 measures look great. You meet the targets. We look at the total phosphorus concentrations. There are differences visible. The dredged compartments have higher total phosphorus concentrations than have the phosphorus treated compartments. And there's no difference between the dredged compartments and the control, for example. When we look at sediment cores that were taken from the different compartments, and look at the phosphate release from those cores, it's obvious that phosphate release from cores incubated under anoxia, it's far less in phosphate-treated compartments, in phosphate-treated sediment, than it's in dredged sediments or in control. So we might speculate that perhaps the durability of an solid phase phosphorus fixative in this situation might be more, might be better than in the case of dredging. We should, of course, realize, and we also try to stress this to our water authorities, that there are many different waters out there. And, well, sometimes the waters have a different color. But with different waters, we actually mean that even waters that are in close vicinity to each other might have a completely different history, different hydrology, different use, or whatever. And they could even have a different or deviating chemistry. And especially the water chemistry is of importance when considering metal-based phosphorus inactivation. Of course, it's obvious that height is of importance there. It's obvious that salinity might influence your way of dealing with eutrophication. Alkalinity might be involved, and especially humic substances can interfere with your metal salts. It's well known and already for a long time that humic substances can complex metal ions, especially the protonate, carboxylic, and phenolic groups in humic substances, and donate electron pairs to metal ions, so providing them a warm bed. And by doing so, those metal ions will be unavailable for precipitation with oxygen ions like phosphates. The figure given here is from a very simple experiment in which we tested the effect of the lanthanum-modified bentonite on phosphate removal in the absence of black dots and presence of the white dots of humic substances, here given as DOC. But this is a rather normal DOC value for Dutch inland waters. The red line gives the expected residual phosphate concentration. So the dosage was such that there was still sufficient phosphate remaining to be measured. In the control, it takes about 6 weeks before the majority of the phosphate is precipitated with the lanthanum, as one would expect. However, in the presence of humic substances, this value is not reached in 6 weeks, and we don't know if it will be reached later on, but it shows that humic substances do interfere with the precipitation of metals with phosphates. There is also some evidence about interference of humic substances in the literature. There's a publication by Jeroen Geurts and co-workers that appeared in Ecological Engineering 2011. They treated peat and different sands with lanthanum-modified clay, which is phosphate in this case, at a recommended dose, recommended by the manufacturer, and 5 times higher dose. And they also flooded the different soil types and incubated them for a reasonable time, about 180 days. The middle panel gives the pore water phosphate concentration and of flooded peat, so with water on top of it, and the most right figure gives the phosphate concentration in the overlaying water, in the surface water. What's obvious in these two graphs is that the phosphate concentrations increase over time, even in a 5 times higher dosing as was recommended by the manufacturer of the modified clay. the increase is equal to that in the control. So this means that there's virtually no depletion of the phosphates, especially not in the overlaying water. In contrast, when they use a sandy soil, phosphate concentration, especially in the 5-time higher doses, which is the lowest line here, and in the overlaying water, which is down there, it's significantly lower than in the control. So, from this study, we might derive that this phosphate performed far worse in a peat environment, and those environments, in general, are considered rich in dissolved organic carbon. So, I put in this slide just recently because some of my colleagues want to use it also in a presentation. We use this kind of information to come to decision support systems. Sorry, this is handwritten one. This one is also in Dutch. These are things flow schemes we offer to our water authorities. One of the things that we think that should be included is that one should include the water chemistry as well, and one should include proper assays, and eventually it all comes down to not one water body is the same. So this means that you will need a rather tailor-made solution to your specific water body. This is a kind of regime shift in the thinking of our Dutch water authorities, where in the past copy-paste of techniques was rather common. Techniques that appeared successful in one system were just copied and implemented on another one. But this might not be the most wise approach. So what our research is, where our research is aiming at now, is we are trying to figure out how we can improve phosphate removal and fixation also in the UC-rich waters. And one of the things that can be done, and which works pretty well in a laboratory environment, is to flocculate the humic acids with the flocculant. So we are now studying that more in detail and hope to come up with some tools for our water authorities that they can also apply in those systems if the system analysis points to that. Well, brings me to the end of this nice video, and actually I'm happy with that because I'm dying for a coffee. And to summarize, we got good results in tackling internal loading and also precipitating developing cyanobacterial bloom in isolated, rather deep systems. We are studying similar approaches in more shallow waters, where of course wind suspension is involved, water chemistry is of crucial importance there. We aim at opening windows for submerged macrophytes to pop up. By doing so, we need experiments on all kinds of different scales, not just in the laboratory, not just in tiny enclosures or some larger compartments, but also experiments on the scale of a whole water body. I think we've only scratched the surface of the possibilities we have in applying all kinds of solid phase phosphate fixatives, and it looks, even for our country, for certain water bodies, promising that the situation can be improved. However, we have also need to be realistic that in quite a few of the waters in the Netherlands, I'm afraid that for the next years or decades, the color will still be red instead of green or blue. Oh, thank you very much for your attention. And if you have any questions or comments or whatever, my email address is down there, and I will be happy to to answer your questions as good as possible. Well, thank you very much for watching, and bye bye.